Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Computational Gas Dynamics. In the week 2 lecture, we are looking at normal shock and oblique shock waves, and this particular lecture is for an oblique shock part 2, and in this lecture we will mainly deal with the oblique shock relations what we have covered in our last class, and also we want to introduce the graphical representation of oblique shock in a curve what that is called as theta beta curve, theta beta Mach number curve. Theta stands for flow deflection angle, beta stands for shock wave angle, m stands for upstream Mach number. Now, let us revisit what we have studied in the in our oblique shock lectures. And an oblique shock is a naturally occurring phenomena in which a supersonic flow can turn towards the main bulk of flow through a flow deflection angle. As you see in this figure, a supersonic flow while crossing this oblique shock gets a turning angle theta, and this turn is towards the main bulk of flow. Whereas, the normal shock is a special case of oblique shock family in which streamlines are perpendicular to the shock waves. Now, if this oblique shock is a straight line, vertical straight line, and it becomes a normal shock, and we call this as a standing normal shock. The streamline that passes through this are always perpendicular to this normal shock. So, hence we can regard it as that a strong oblique shock qualifies to be a normal shock, whereas the weakest possible oblique shock could be a Mach wave, because the Mach wave is the initiation of the compression events, and when the Mach wave starts forming, it gives the indication that the compression waves are going to be stronger and stronger, and they will be termed as oblique shock. Now, for the oblique shock, they are straight but inclined and angle to the upstream of the flow, known as flow deflection angle, and of course, this angle is always higher than the Mach angle. So, whatever I have discussed so far, definition of Mach angle is given by mu m, that is sine inverse of 1 by m. So, this Mach angle is shown here, that is with respect to Mach wave. Now, this Mach wave when becomes stronger, this turns out to be an oblique shock. So, when it is a oblique shock, the m2, that is Mach number across after the oblique shock, is stronger than this corresponding Mach wave. But however, this Mach number after this oblique shock has a lesser value than that of m1, which is the upstream Mach number. And for oblique shock wave angle, beta is always greater than mu m, and for normal shock, this beta is equal to pi by 2, 90 degree. In our last segment, we derived the oblique shock governing equations, and those governing equations are controlled by the parameters. That is, if you look at oblique shock, what we know is that upstream conditions in which the flow is supersonic, and the downstream conditions we have unknown conditions, but they have much higher value than that value of upstream value. But main controlling parameter for this oblique shock is this particular equation, that is tan theta is equal to twice cot beta whole bracket m1 square sin square beta divided by m1 square into bracket gamma plus cos 2 beta plus 2 bracket n. So, here theta stands as the flow deflection angle, beta stands as this shock wave angle, and m1 stands as Mach number. So, that means for a given Mach number we need and if you want to calculate the shock wave angle we need information how the flow gets turned. So, once you know this, then we can correlate this oblique shock information with respect to a normal shock information by introducing normal shock Mach number before the shock and normal shock Mach number after the shocks. So, this Mn1 and Mn2 decides decides the equivalent nature of a normal shock corresponding to this particular oblique shocks. Then we know the relation between beta, theta and we can get the information about the Mach number M2. So, once we know this Mach number M2, then we get this M2 number, but the density conditions, static density ratio, static pressure ratio, static temperature ratio, all can be find out corresponding to equivalent normal shock Mach number Mn1. Then also we can find out entropy change across the oblique shocks. So, what we have discussed so far that this theta beta m relation and this normal shock Mach number and M2 calculations gives the complete information for an oblique shock. Now, once we know for a given upstream Mach number, if you know this corresponding normal shock Mach number, then you can use this normal shock table for that corresponding Mach number and we can calculate all desired properties, static pressure, temperature and density ratios, again stagnation pressure, temperature, stagnation pressure and ratios and all. And of course, we can also equally calculate M2 and here this M1 is treated as Mn1 for an oblique shock analysis, M2 treated at Mn2. And when you have Mn2, we can get back M2, which is this. When you know once you know M1, we can calculate Mn1, which is this one. So, that way we can get this information. So, this is what we say about the oblique shock relations mathematical part. Now, there are another method that this relations, trigonometric relations, that is theta beta m1 relation can be represented graphically. So, in one axis what we plot is that is in the y axis it is called as shock wave angle beta. In the x axis the flow deflection angle is plotted. Now, what we do, you give you take like fix a Mach number. Let us say I am fixing the Mach number of 2 and once I fix the Mach number and keep changing theta and calculate beta. So, this particular plot, this is for m is equal to 2, that can be plotted. So, we can get one plot which is for m is equal to 2. Then similarly, that is for different value of theta we can keep doing. And similarly, if you can keep on increasing the Mach number, let us say we are talking about Mach 5. So, Mach 5 refers to this particular curve and we are keeping on changing the flow deflection angle and find the corresponding shock wave angle. So, likewise there will be infinite number of curves that can be drawn for a given values of Mach number and flow deflection angle. So, how to use this curve? For example, instead of looking into complicated trial and error method for solutions, if you for a given problem normally the flow deflection angle is given, Mach number is given. So, we can choose a particular Mach number. Let us say Mach number is 3, then we can take this plot as Mach 3 and if you the flow deflection angle is 25, then for this 25 degree wherever it crosses or touches this Mach 3, we can drop a perpendicular at this point. So, this will be a value of beta 1. Another value also we can extend this curve and it crosses here. So, this value we can drop a normal onto it. So, this will be another beta 2. That means, what it says is for a given Mach number there are two possible values of beta. That is one aspect. Another so later point of time we will say higher beta means higher beta means shock is stronger. Now for let us say there are some situations where we will find that when you say Mach flow deflection angle is 30, Mach number of 2. So, flow deflection angle 30, Mach number 2, which means that Mach number 2 curve is here. That means Mach number 2 does not qualify for theta is equal to 30. At Mach 2 there is no oblique shock solution possible. Similarly, for flow deflection angle 30, if you say Mach number of 3, then we do not have any curve for this Mach number. That means for Mach 3 with flow deflection angle 35 degree, the oblique shock solution is not possible. So, these are the some critical inferences that we find from this curve. Now, let us see how it means to us physically. So, here the same thing here, another observation that I can say that if here if you look at some points, peak points A1, B1, C1, D1, E1 and F1. So, that means for a given Mach number there is a peak point where we have which demarks the strong shock and weak shock situations. So, we say that here M2 is less than M1. Now, this M2 less than M1 means M2 can be also less than 1. So, we can be subsonic and M2 can be less than M1 where flow is supersonic, and this happens in the downstreams. So, these are the two possibilities, extreme possibilities of this Mach number in the downstreams. So, this particular case refers to a strong shock situation, and this particular case refers to weak shock. Now, for a given flow deflection angle, if you are moving from strong shock from weak shock to strong shock, one particular point there is a transition. Transition means Mach number in the downstream becomes stronger and stronger, where you have Mach is equal to 1. So, at those points, that is point A1, B1, C1, D1, E1 and F1, these are the locus of points demarking strong shock for which M2 is less than 1 and weak shock where M2 is greater than 1, and for this case your theta should be less than theta max. That means we must have oblique shock solutions. So, this will be true for m is equal to, this is for this m is equal to 2, where theta is less than theta max is the location at that point, maximum possible flow deflection at that point, and these points represent those strong and weak shock conditions. Another situation we have locus A2, B2, C2, these are locus of all points joining theta max. So, A2 for every curve that will be the maximum theta max. So, for this Mach 2 curve we can drop a vertical and that will be regarded as theta max. This is for Mach 2, and for let us say Mach 2.5 theta max falls here. So, these are the maximum flow deflection angle that is possible for that corresponding Mach number. So, this is the critical features that we obtain from the while drawing these oblique shock curves. Now, let us find out the important physical significance for these situations. So, we call this as a inference number 1. So, first inference that we get or first conclusion that we get from the curve is that for a given Mach number there exists a maximum possible flow deflection angle, and in a physical geometry having a deflection angle higher than the maximum value, there is no oblique shock solution for a straight oblique shock. So, which means that if in a particular physical geometry, let us take this particular case that we have a wedge in which a supersonic flow is encountering a wedge. Now, this wedge has some angle theta. So, theta, and for this theta and for this Mach number, we have a upper limit which is called as theta max. Let us say m1 is equal to 2.5. So, for 2.5 we can have this upper limit max is theta max. That means, for m1 is equal to 2.5, from this curve theta max is equal to, let us say, 30 degree. Okay. So, this solution we get independently from this theta beta m curve. Now, in a physical geometry which is a wedge here and the supersonic flow passing over it, and here this angle, if you say that this theta is greater than theta max, that means if it is more than 30, that means we do not have a oblique shock solutions. So, we cannot have this theta max with this oblique shock curve we cannot use. So, there what happens physically, what happens? So, since there is no oblique shock solution possible, we will encounter a detached shock. That means, oblique shock is nowhere attached to this. So, it will remain as a detached shock, and that means the shock wave stands at certain distance from the tip of the wedge. So, this is what we say standoff shock standoff distance. So, what it says, in such cases shock wave will be curved and detached, and it is commonly known as bow shock, and this bow shock has a great resemblance that it behaves as a normal shock. So, this is first inference that we get. Now, we will go to second inference. Now, you say that if your for that same case which is 30 degree here, that means for m1 is equal to 2.5, theta max is equal to 30 degree, but in a actual wedge situation, if your theta is less than theta max, that means if this angle is less than 30 degree, so this oblique shock will remain attached. So, how this streamline will behave? Streamline will have touch this oblique shock, it will get deflected by an angle theta, that is m2, it gets deflected by angle theta which is parallel to this wedge surface. Now, for this theta there are two oblique shock solutions possible for a given Mach number and flow deflection angle. Now, let us say we have m1 is equal to 2.5, theta is equal to theta max. Now, but your theta max is this, but if your actual angle, let us say this theta is, let us say, 20 degree. Okay. Now, if your actual wedge is 20 degree, so for a Mach number of 2.5, so Mach number of 2.5, that is curve B, with theta is equal to 20 degree, theta is equal to 20 degree, we have 2 points that this line touches this Mach 2.5 curve. Okay. So, one angle, that is for theta is equal to 20 degree, m1 is equal to 2.5. So, this will give beta minimum and beta maximum value. So, this minimum value corresponds to, so this number will be approximately 42 degree, this number will be approximately 80 degree. So, minimum value will be 42 degree and the maximum value will be 80 degree. So, in other words, what we can say, this attached shock has two possible solutions for which beta can be this beta mean and this beta can be this beta max. So, one is 80 degree, other is 42 degree. So, here that says that for this case there are two solutions for a shock wave angle for a given upstream Mach number. So, one we call is as a weak shock, other we call as a strong shock. So, a more clear picture is shown here, that means for a given theta we have a weak shock, we have on given Mach number there are two possibilities, one is a weak shock solution and that is a strong shock solution. So, out of this the weak shock is mostly favored for a natural occurring process, since the strong shock is generally governed by the back pressure through independent mechanisms. So, those things we will cover later, but by default assumption is that we have to take that value for weak shock solutions. So, you have to take m1 theta where beta should be beta minimum. You take beta minimum value that we get from here, that is 42 degree at m is equal to m1 is equal to 2.5, theta is equal to 20 degree. Next inference is that for attached shock situation, the weak oblique shock is always straight and attached to the body. Now, if we have this attached shock and this is a weak oblique shock, and theta is equal to theta less than theta max, the Mach number after the weak shock solution is always supersonic. That means, m2 is greater than 1, but m2 is less than m1. So, this is what we call as a weak shock solution. Now, in the domain of strong shock solution, what we see is that the strong shock solution always gives a subsonic Mach number after this shock, and mainly happens in the vicinity of maximum flow deflection angle. Now, when we have a strong shock solutions for same m1 and same theta, so in our last example for m1 is equal to 2.5, theta is equal to 20 degree, you have beta max turns out to be 80 degree, which is here. This means if your beta is 90 degree, it resembles a normal shock. Now, in this particular case we get beta is 80, that means the strong shock solution behaves as a normal shock, and for this case when you have a strong shock, your m2 will be less than 1. So, what it means that if you take this maximum flow deflection angle for every curve is A2, B2, C2. Any solutions above this refers as a strong shock. Any solutions below this we say it is a weak shock region. And which point separates this point A2, B2, C2, D2, E2, which is the important point for theta max corresponding to upstream Mach number M1. Then next inference, at 0 flow deflection angle, when your beta is 0, that means when theta is equal to 0, when theta is equal to 0, so this solution will give you beta to be 90 degree. So, this resembles to a strong normal shock with significant pressure difference between the upstream and downstream. A weak oblique shock becomes a Mach wave, that means when if you put when becomes a Mach wave when the shock wave angle is equal to Mach angle, when beta is equal to mu m. So, mu m means let us say for a given m1, so let us say m1 is equal to 2. So, mu m will be sin inverse 1 by 2, that 1 by 2 sin inverse 1 by 2. So, for this m1 is equal to 2, theta is equal to 0 degree, which means this angle, this is the 0 degree, we can say mu m happens to be 30 degree, which is shown here. So, this that means for every Mach number the vertical axis starting point refers to mu m, that is Mach angle, and it is a situation where there is a very small pressure difference. Next inference is that for a given flow deflection angle, for a fixed flow deflection angle, as the free stream Mach number decreases from high to low supersonic value in the weak shock solutions. So, weak shock solution refers the location of A1, B1, T1. So, A1, B1, C1. So, let us draw a demarcation, drawing a line A1, B1, C1. So, this line refers to demarcation of strong shock solution and weak shock solution. Now, in this weak shock solution region, if we are increasing the Mach number, that means we are going vertically. So, here in this curve, when we are going vertically, the Mach number decreases from high to low supersonic value. So, in this case Mach number drops from Mach 8, which is at this point, to Mach 2, and we are moving along same flow deflection angle, but in the weak shock region. So, what happens? The shock wave angles increases. So, if you go, that means as you go and higher Mach number your Mach number drops, but the shock wave angle increases, that means shock becomes stronger and stronger. So, this is the inferences that we get. So, after going through all the inferences, then we got the catch that how to control an oblique shock. So, we call them as a controlling parameters. So, in this, now if you look at this equation, that is theta beta m1 relations, one thing, it depends, an oblique shock can be controlled, that means beta can be controlled by two parameters, one is through theta, other is through Mach number, and we have seen what happens if you are changing theta and what happens if you are changing Mach number. So, when the normal component of Mach number ahead of the shock wave increases, the strength of the shock wave also increases. Normal component of Mach number can be increased by increasing the shock wave angle, though higher through higher flow deflection angle. The other possibility of increasing the normal shock component of Mach number can be achieved by increasing the upstream Mach number. So, as a rule of thumb, when the flow deflection angle increases, keeping upstream Mach number constant, the shock wave angle increases. When the upstream Mach number increases, keeping flow deflection angle constant, the shock wave angle decreases. So, this is the main important controlling events that we can do so that we can change the shape of the oblique shocks. So, this is the part 1 of the lecture. Now, I will cover to the part 2 of this lecture. So, in the second part of the lecture, we will now focus the analysis of theta beta M curve. So, in this previous part, we have mainly emphasized about theta beta M curve. Now, let us see how we can do this analysis with a given numerical problems. So, for a given problem, we are trying to change different parameters and try to see whether the oblique shock is getting stronger or weaker. So, the first problem we are looking at that a uniform supersonic stream at Mach number 3 is and pressure 90 kPa and 290 Kelvin is deflected through a compression corner by an angle 20 degree. So, you have to calculate the downstream parameters, that is shock wave angle, Mach number, static and stagnation properties. So, similar type of problems we have also solved in our previous lectures, but there we gave more emphasis on looking at the trigonometric relations, but here we will try to solve the problems through this theta beta M curve. So, if you for this problem, first thing you draw that what is the given flow geometry. So, we have a compression corner and in that compression corner the flow, this angle is 20 degree and the supersonic flow is passing through this corner. So, obviously, it will encounter an oblique shock. And here conditions that are given, M1 is equal to 3, P1 is equal to 90 kPa, T1 is equal to 290 Kelvin, and downstream parameter with the and since this is this streamline when it crosses, so it will get deflected and that deflection angle will be flow deflection angle, that is theta is equal to 20 degree. And because of this flow deflection, there will be an oblique shock, that is, and it stands as beta, as a beta, which you do not know. Now, here we have M2. Now, downstream properties are noted as M2, P2, T2, P02, T02, then rho 2, rho 02 and so on. So, we also want to know what is P01, T01, rho 01, all these numbers. So, first thing that we want to do, that to get this P01, P02, we say M1 is equal to 2 and isentropic relations gives so these relations give your T01 by T1 is equal to 1 plus gamma minus 1 by 2 M1 square, P01 by P1 is equal to 1 plus gamma minus 1 by 2 M1 square. So, this ratio we get for stagnation to static 36.73, stagnation temperature ratio 2.8, and for given values we can note down P naught 1 is equal to 3305.7 kPa, T naught 1 is equal to 812 Kelvin. Okay. So, this now for this condition, for this we got this thing. Then what information we require is what happens after this oblique shocks. So, we recall our theta beta m curve which is plotted here. So, here what we have to look at, we have m1 is equal to 3, theta is equal to 20 degree. So, take this curve, that is curve C, m1 is equal to 3. So, this curve refers as m1 is equal to 3. Now, from this curve we are looking at theta is equal to 20 degree. So, theta is equal to 20 degree here. So, this curve, so for this weak shock solution we can find it here. So, this when you drop a vertical from this point, so this will be beta will be approximately 37 degree. So, once you know this beta, we can have this relation mn1 is equal to m1 sin beta, that is 1.82. Now, for this m1 we have to refer normal shock table. So, this extract of normal shock table is here. So, m1 is 1.82. So, 1.82 is located at this number. So, this will give you mn2 as mn2 as 0.6121. Then P2 by P1 corresponding to that m1 mn1 is 3.698. T2 by T1 is equal to 1.547. P02 by P01 0.8038. Since we know this P1 T01, P1 T1 and we know these conditions. So, this will give you P2 is equal to 332.8 kilopascal, T2 is equal to 448.6 Kelvin, P02 is equal to 2657 kilopascal. So, all the information now we get for these problems. Flow deflection angle, shock wave angle 37 degree, pressure, temperature values, stagnation pressure. Of course, stagnation temperature do not change, that is 812 Kelvin, it remains constant. Okay. So, this is the first problem that we solve for this oblique shock using this theta beta m curve. Now, with the same data, if the flow deflection angle is increased to 30 degree, then we have to solve this question 1, solve for shock wave angle, Mach number, static and stagnation property, and you have to compare the results for question 1. So, here we carry forward this data, that is m1 is equal to 3 and we have given problem now shifts to this this theta is now 30 degree. We will have an oblique shock. So, it will have a different values of beta. Streamline will be deflected by an angle after crossing this oblique shock up through this angle 30 degree. Your M1 remains as 3. So, we need to find out what is the new value of beta when the streamline is deflected. So, for M1 is equal to 3, we carry forward the data. We have P1 is equal to 90 kPa. We have already calculated this. P01 is equal to 3305.7 kPa. T1 is equal to 290 Kelvin. T01 remains as 812 Kelvin. So, with this data, when your theta is 30 degree and M1 is equal to 3. So, theta is equal to 30 degree and M1 is equal to 3, that is you have to go along this curve C, and weak shock solution stops here. So, it is just above 50 degree. So, if you drop a vertical for this on the point A, so this angle is closely related to 52 degree. So, beta now becomes 52 degree, that we get from this theta beta M curve. So, since beta the previous beta it was 37 degree. So, beta now increased from 37 to 52 degree. So, that means this is a stronger shock, which means this is what we say compare the results. So, the shock wave becomes stronger because the flow deflection angle is increased. So, theta goes from 20 to 30 degree. So, it becomes shock wave becomes stronger, and then rest of the analysis will be similar. So, we can have Mn1 is equal to M1 sin beta. So, here this value would be 2.36. So, we refer this normal shock extract shock table, and we have to look for Mn1 is equal to 2.36. So, 2.36 is somewhere here close to 2.35. So, this will give you Mn2 is equal to 0.5286. So, once you know Mn2, we can calculate M2. M2 is equal to Mn2 by sin beta minus theta, and this value stands now as 0.41. So, if you look at previous value of M2, for that is for theta is equal to 20 degree, we had M2 is equal to 2.09. So, here M2 becomes 0.41, that means M2 is subsonic. Which means we have a stronger shock. Then rest of the things we can calculate, that is P2 by, for this particular line, these values can be noted from the on this line. So, we have P2 by P1 is equal to 6.28, T2 by T1 is equal to 1.993, P02 by P01 0.5615. So, this will give you P2 is equal to 562.5 Kelvin, P2 is equal to 562.5 kilopascal, T2 is equal to 578 Kelvin, P02 is equal to 1856 kilopascal. So, you can say there is a larger pressure drop, total pressure drop for these problems. So, in summary, what we can say, when theta value increases, the shock wave becomes stronger and it approaches towards the stronger shock solutions with larger total pressure drop. Now, in the third problem, for the same situations, here we are increasing the Mach number. So, for the same problem, that is compression corner, theta remains 20 degree. So, now the Mach number is equal to 5. The streamline will also get deflected. We have same P1 90 kPa, T1 290 Kelvin. So, obviously, there will be an oblique shock which is beta. For this oblique shock, the angle would be, shock wave angle will be beta. So, for this particular Mach number, now here catch is that we are increasing Mach number from 3 to 5. So, basically Mach number from this theta beta m curve, we have to look for Mach number of 5, that is curve B, and theta is equal to 20 degree. So, theta is equal to 20 degree, curve E. So, at this point, M1 is equal to 5, theta is equal to 20 degree, weak shock solution gives beta to be 30 degree, which means the shock wave angle decreases with increasing the Mach number. So, the shock is a weaker shock. That means, with respect to Mach 5, theta 20 degree, it is a weaker shock, but it was a stronger shock for Mach is equal to 3. That is what we get this information. This we get from theta beta m curve. Now, if you recall our previous data, M1 is equal to 3, P1 is equal to 90 kPa, P01 is equal to 3305.7 kilopascal, T1 is equal to 290 Kelvin, T01 is equal to 812 Kelvin. So, these are the data, and for these things, once you know this beta, we can calculate Mn1, M1 sin beta, that is 2.5. So, take this normal shock table for Mn1 is equal to 2.5 at this value. So, this will imply Mn2 is equal to 0.513, which is this. Then we can find out M2 is equal to Mn2 divided by sin beta minus theta. So, this value is now 2.595. So, this is also M2 is less than M1, but M2 is greater than 1. So, it is a supersonic flow. So, in last previous case shock was stronger, and so it's because for which M2 is less than 1, flow is subsonic, but in this case shock is weaker and but flow is still supersonic. And now for this case we have this ratio P2 by P1 7.125, T2 by T1 that is 2.137, P02 by P01 that is 0.499, and these ratios will imply absolute values as P2 is equal to 641.25 kilopascal, T2 is equal to 620 Kelvin, P02 is equal to 1649.5 kilopascal. So, this complete analysis for 3 problems gives the complete flow picture what we analyzed through this theta beta m curve. We saw that in this particular problem, when you compare the results, the first was the conventional problems for m is equal to 3 and theta is equal to 20 degree. In the second problem, keeping m1 same, we increase theta to 30 degree. We say that the shock wave becomes stronger. In the third problem, what we did, keeping theta to be 20 degree, we increased m1 from 3 to 5. So, there we say that flow is, the shock wave becomes weaker. So, basic summary is that this theta beta m curve controls the oblique shock characteristics, or you can say theta beta m relations controls this oblique shock characteristics. So, that characteristics can be controlled, oblique shock locations, whether it will be attached or detached, that can be controlled by upstream Mach number and the flow deflection angle. So, with this I conclude. Thank you for your attention.